Hello. Now I will do the second law of Kirchhoff. So just like first law was based upon the conservation of charge, the second law is based upon conservation of energy. Conservation of energy. So what happens in case of circuit? A circuit will always be having a battery. So when there is a battery, there will be one electrical component, at least there will be one electrical component, and then you will see some resistive component. In some other cases you see capacitive component as well, and in some other cases you will see inductive element as well. So that's how there will be a circuit. And it will be a complex structure. It's not like all the elements will be connected in series. It's not like that. It can be a complex structure. Now, more about this C and L we'll learn in later lectures. Right now, I'm just representing these so that we should have an idea about the second law. Okay. So what happened when this is a circuit? This electrons in the circuit, they keep moving. The electron in the circuit, they keep moving in the circuit. They keep crossing the inductors, they keep crossing the capacitors, and they keep crossing the resistances, and they keep crossing the battery. These are the electrons. So when these electrons are moving, obviously there have to be a force applied onto these electrons, that's why they are moving, or there have to be some potential difference applied across the circuit, that's why these electrons are moving. Or what happened? Basically, these are the electrical instruments, electrical elements, like battery is there, resistance is there, capacitor is there, and the inductor is there. Okay, so the movement of electron, it starts from the battery. So what happened? Battery, which is having a chemical potential energy, this battery which have chemical potential energy. This chemical potential energy of the battery gets transferred to the electron, and this chemical potential energy gets converted into the mechanical energy of this electron. And mechanical energy, I should say mechanical energy is a combination of kinetic energy and the potential energy. So this chemical potential energy of the battery, which is inside the chemicals, in terms of chemicals, basically this battery, which is the DC battery, it has some chemicals. So inside those chemicals, there is a chemical potential energy. So that chemical potential energy gets transferred to the electron in terms of mechanical energy, or to be more precise, in terms of kinetic energy of the electron. After getting this kinetic energy, electron starts moving. Okay, and when they start moving, they keep losing or gaining. Both the things happen actually. They keep losing or gaining this kinetic energy across each and every element, electrical element, whether it is an inductor, whether it is a capacitor, or whether it is a resistance. They keep gaining or losing their kinetic energy. And when these electrons comes back to their original position, the kinetic energy of the electron, it is always same. Because see, I'm talking about the mechanical energy of the electron, I'm talking about the potential energy of the electron, or I'm talking about the potential energy of this circuit. Inside this circuit, in this circuit, if you see, the forces, which is the electrostatic force mainly, or the magnetic force, the movement of electron is happening because of the electrostatic or magnetic force. These are conservative forces. So the movement of this electron is happening under the influence of conservative forces and conservative forces alone. So when they gain or lose kinetic energy, or when they gain or lose their potential energy, when they will come back to the same location, their potential energy will be same, their energy will be same. Because see, they are moving under the influence of conservative forces alone. There is no non-conservative force, and we already know in case of work, power, and energy, we learned that in that chapter, when there is no non-conservative force applicable onto a system, and when there is no external agent applicable onto the system, then the potential energy is a state function. A state function means potential energy depends upon the location. So once you choose the location, potential energy of that location does not change. Okay, so potential energy is a function of location. So when you come back to the same location, its potential energy, or you can say its potential, will be same. So if I calculate the potential of this point, or this point, or this point, it is not going to change ultimately. The potential in this circuit, this is a simple circuit, in this circuit or in the complex circuit, potential in a complex circuit at a particular point is not going to change, because conservation of energy. So ultimately, the kinetic energy will keep changing into potential energy, which will keep changing into some other form of energy. But ultimately, when you come back to the same location, energy is not going to change. Okay, so that's your second law, the meaning of second law. The definition, when we talk about the definition of second law, it is in terms of potential. So you say, when you calculate the potential over to a whole closed circuital loop, it comes out to be same. Or you can say potential difference calculated over to a closed loop is always zero. So when you keep calculating the potential difference across each and every element, and when you come back to the same location, the value of potential difference will always be zero, because ultimately there are no non-conservative forces which are acting into the system. Like in this case, if I define this point A, this point as B, this point as C, this point as D, and ultimately, okay. So you see, in this case, if I define and if I calculate VA minus VB, it will be having some value. We already know if the current is flowing in this direction, we know how to calculate VA minus VB. It will be minus IR. When you calculate VB minus VC, it is generally plus Q by C. I'm assuming positive charge here. And then you calculate VC minus VD. It will be, you can calculate that LDI by dt. So I'm not concerned right now onto the right hand side. And then you calculate VD minus VA. You see, when you move from this point to this point, there is no potential difference, because ultimately there is no electrical element there. But once you cross this battery, there is a element. So if you add the left hand side, so ultimately this is potential difference across one element, this is potential difference across another element, the third one is also a potential difference across the third element, and this is the fourth element. So you calculate the potential difference across each and every element. But when you add everything, so you see, everything gets cancelled out. And this cancelled out by this. So this becomes zero. So potential difference in a closed loop, summation of potential differences in a closed loop is always zero. That's your second law. Potential difference in a closed loop, whether that loop consists the battery or not, it doesn't matter. Whatever electrical circuits, whatever kind of electrical circuit it is, whatever kind of electrical element it consists, it doesn't matter at all. Whenever you are going to calculate the potential difference in a closed loop, the value will always be zero. So potential difference in a closed loop will always be zero. When you calculate the summation, it is going to be zero. That's your second law, because energy is always conserved. You can change the form of energy, but you cannot destroy the energy, you cannot generate the energy. It's only its form gets changed. It does not get destroyed, it does not get generated. So at a point, if you calculate the total energy, it is going to be the same ultimately. So if you calculate the VA minus VA, it is always zero. Okay, if the conservative forces are being applied. So when we want to apply the second law, all we need to learn is how to calculate these right hand sides. So basically, when we are going to cross a electrical element, how the potential difference is to be calculated across that electrical element, that's what we need to learn. So if we have that, because ultimately this left hand side will always be zero. If we know how to calculate this right hand side corresponding to every movement, in that case we will be making multiple equations using the second law. It will help us to solve the complex circuit problems. Okay, so in the next lecture we will learn how to calculate these values, basically how to calculate the potential difference when we are going to cross the electrical elements like resistance, like battery, like capacitor, and like inductors. The thing is, capacitor and inductor we'll do later on. In this chapter we'll be concerned about R and E. Okay, thank you.